Okay, welcome to the chapter on light. This will have two parts. So this will be part one. Light is the only thing you see. All visible objects either emit or reflect light. Almost everything we see is made visible by the light it reflects. Some materials such as air, water, or window glass allow light to pass through. Other materials such as thin paper or frosted glass allow the passage of light in diffuse directions so that we can see objects through them. Scientists now agree that light has a dual nature, part particle and part wave. It's one of the few things in the universe that behaves as both a particle and a wave. Light has been studied for thousands of years. Some ancient Greek philosophers thought that light consisted of tiny particles, which enter the eye to create the sensation of vision. Others thought that vision resulted from the streamers or filaments emitted by the eye making contact with an object. Up until the time of Newton and beyond, most philosophers and scientists thought that light consisted of particles. However, one Greek, Empedocles, thought light traveled in waves. One of Newton's contemporaries, the Dutch scientist Christian Huygens, I can't pronounce his name, also argued that light was a wave. So here's where we get into the big argument of particle and wave. The particle theory was supported by the fact that light seemed to move in straight lines instead of spreading out as waves do. This showed that under certain circumstances, light does spread out, and other scientists found evidence to support the wave theory. The wave theory became the accepted theory in the 19th century. In 1905, Einstein published a theory explaining the photoelectric effect. According to this theory, light consisted of particles called photons. These are massless bundles of concentrated electromagnetic energy. Scientists now agree that light has a dual nature, part particle and part wave. So what is the nature of light? Well, it's two parts really. Michelson's experimental value for the speed of light is 299,920 kilometers per second, which is usually just rounded to 300 kilometers per second. Or we a lot of times say 3 times 10 to the 8th meters per second. This is our standard for speed of light. It was not known whether light travels instantaneously or with finite speed until the late 1600s. Galileo tried to measure the time a light beam takes to travel to a distant mirror, but it was so short he couldn't begin to measure it. Others tried the experiment at longer distances with lanterns they flashed on and off between distant mountaintops. All they succeeded in doing was measuring their own reaction times. The first demonstration that light travels at a finite speed was supplied by the Danish astronomer Olaus Romer about 1675. He carefully measured the periods of Jupiter's moons. The innermost moon, Io, revolves around Jupiter in 42.5 hours. The Io disappeared periodically into Jupiter's shadow, so this period could be measured with great accuracy. He found that while Earth was moving away from Jupiter, the periods of Io were all somewhat longer than average. When the Earth was moving toward Jupiter, the measured periods were shorter than average. He estimated that the cumulative discrepancy amounted to about 22 minutes. Light coming from Io takes longer to reach Earth at a distance d than a position A. The extra distance that the light travels divided by the extra time it gives the speed of light. So he did this as you're traveling away from. If you're going away from, it takes longer. If you're going toward, it's shorter. So you could figure out the speed of light. He correctly interpreted this discrepancy. The Io passed into Jupiter's shadow at the predicted time. The light did not arrive until it had traveled the extra distance across the diameter of Earth's orbit. The distance is known now to be 30,000 kilometers, or 300,000 kilometers. Sorry, 300 million kilometers. Using the travel time of 1,000 seconds for light to move across Earth's orbit makes the calculation of the speed of light quite simple. The speed of light equals our distance divided by time. Excuse me. The extra distance traveled divided by the extra time gives us the 300,000 kilometers per second. The most famous experiment measuring the speed of light was performed by the American physicist Albert Michelson in 1880. Light was directed by a lens to an octagonal mirror. a beam of light was reflected to a stationary mirror on a mountain 35 kilometers away and then reflected back. The distance was known, so Michelson had to find only the time it took for them to make a round trip. When the mirror was spun, short bursts of light reached the stationary mirror and were reflected back to the spinning octagonal mirror. If the rotating mirror made 1/8 rotation while the light made the trip, the mirror reflected light to the observer. If the mirror was rotated too slowly or too quickly, it would not be in a position to reflect the light. Okay, here we go. The light is reflected back to the eyepiece when the mirror is at rest. Here's the experiment. Reflected light fails to enter the eyepiece when the mirror spins too slowly. So it just reflects off, it doesn't do it right. Or if it goes too fast, it's also not going to reflect the right way. When the mirror rotates at the correct speed, the light reaches the eyepiece, and then is able to reflect back. When the light entered the eyepiece, the time for the light to make the trip and the time for the mirror to make 1/8 of a rotation were the same. Michelson divided the 70-kilometer round trip distance by this time and found that the speed of light was 299,920 kilometers per second. Like we said, is usually rounded to 300,000 kilometers per second. He won the Nobel Prize in 1907 for this experiment. The speed of light in a vacuum is a universal constant. Light is so fast that if a beam of light could travel around the Earth, it would take 7.5 trips in 1 second. Light takes about 8 minutes to travel from the Sun to the Earth, and 4 years for the next nearest star, Alpha Centauri. The distance light travels in 1 year is called a light year. Alright, here's your think question. Light entered the eyepiece when Michelson octagonal mirror made exactly 1/8 of a rotation during the time light traveled to the distant mountain and back. Would light enter the eyepiece if the mirror turned 1/4 of a rotation in this time? Question. Yes, light would enter the eyepiece whenever the octagonal mirror turned in multiples of 1/8 rotation. So if you did a quarter or a half or 1, etc., in the time the light made its round trip. What was Michelson's experiment? Value for the speed of light. The electromagnetic spectrum consists of radio waves, microwaves, infrared light, ultraviolet rays, X-rays, and gamma rays. This is the entire spectrum. Light is energy that is emitted by accelerating electric charges, often electrons in atoms. The energy travels in a wave that is partly electric and partly magnetic, such as we call it the electromagnetic wave. Light is a position of the family of electromagnetic waves that includes radio waves, microwaves, and X-rays. The range of electromagnetic waves is called the electromagnetic spectrum. If you look at this, it's kind of split into groups. If you see this right here, that is light. That's the light that we see from the electromagnetic spectrum. It is very, very small part of the electromagnetic spectrum. If you look at this, radio waves is huge, microwaves is huge, infrared waves is huge. Light is very, very, very small. UV light is pretty big. X-rays are also very small, or gamma rays are pretty big. This light is the visible light that we see and how we see the colors and different things like that. So it's of the electromagnetic spectrum that we're talking about, what we can actually see is a very small part. The lowest frequency of light we can see appears red. The highest visible light, violet, has nearly twice the frequency of red light. Electromagnetic waves of frequencies lower than red of visible light are called infrared. So anything lower than red is infrared. Heat lamps give off infrared waves. Electromagnetic waves of frequencies higher than those of violet are called ultraviolet. They are responsible for sunburns. So any light, any electromagnetic light below red is infrared. Above violet is ultraviolet. What are the waves of the electromagnetic spectrum? Remember, it's radio waves through gamma. Light passes through materials whose atoms absorb the energy and immediately re-emit it as light. Light is energy carried in electromagnetic waves, generated by vibrating electric charges. When light strikes matter, electrons in the matter are forced into vibration. We talked about this in the earlier chapters, that Basically, sound is something, all waves travel by something that vibrates. Light is also causes vibration. Like my experiment we did in class, just as sound waves can force a sound receiver into vibration, a light wave can force charged particles and materials into vibration. So it's not just sound that does this, light can do it also. Exactly how a material responds to light depends on the frequency of light and the natural frequency of the electrons in the material. Visible light vibrates at a very high rate, more than 100 trillion times per second. To respond to this ultra-fast vibrations, a particle must have a very little inertia, so very little mass. Electrons, with their small mass, can vibrate very, very fast. Materials that transmit light are called transparent. Glass and water are transparent. Materials that are springy or elastic respond more to vibrations at some frequencies than others. The natural vibration frequencies of an electron depend on how strongly it is attached to the nearby nucleus. The electrons of atoms in glass can be imagined to be bound to the atomic nucleus as if connected by strings. So you see all these are called your electrons, if you remember back from chemistry. And you can think of them just attached by springs and they're kind of bouncing around. Electrons in glass have a natural vibration frequency in the ultraviolet range, so way above a violet. In ultraviolet light, resonance occurs as the wave builds a larger vibration between the electrons and the nucleus, making them bounce more and more. The energy received by the atom can be either passed on to neighboring atoms by collisions or re-emitting as light. The ultraviolet light interacts with an atom that has the same natural frequency. The vibration amplitude is unusually large. The atom typically holds onto this energy for about 1 million vibrations, or 1/1,000,000th of a second. During this time, the atom makes many collisions with other atoms and gives up its energy in the form of heat. That's why glass is not transparent to ultraviolet. When the electromagnetic wave has a lower frequency than ultraviolet, as visible light does, the electrons are forced into vibration with smaller amplitudes. The atom holds the energy for less time, with less chance of collision with neighboring atoms. Less energy is transferred as heat. The energy of the vibrating electrons is remitted as transmitted light. Glass is transparent to all the frequencies of visible light. The frequency of the re-emitted light is identical to that of the light that produced the vibration to begin with. The main difference is a slight time delay between absorption and re-emission. This time delay results in a lower average speed of light through a transparent material. So we said the speed of light is 3.0 times 10 to the 8th. When it goes through glass, it slows down just a little bit. A light wave incident upon a pane of glass sets up vibrations in the atoms because of the time delay between absorption and re-emission. The average speed of light in glass is less than c. C is the variable we use for the speed of light. In a vacuum, the speed of light is constant, 300,000 kilometers per second. We call this speed c, the speed of light. The light travels slightly less than c in the atmosphere, but the speed is usually rounded to what the 3.0 times 10 to the 8th. In water, light travels at 75% the speed in a vacuum, or 0.75 c, so it slows down when it gets to light, which is different from sound. Remember, sound sped up whenever it got to water and solids. Light slows down. In glass, light travels about 0.67 the speed of light, depending on the glass type. In a diamond, light travels only 0.40 the speed of light. When light emerges from these materials into the air, it travels at its original speed, back to the speed of light. Infrared waves with frequencies lower than visible light vibrate not only the electrons, but also the entire structure of the glass. This vibration of the structure increases the internal energy of the glass and makes it warmer. Glass is transparent to visible light, but not to ultraviolet or infrared light. These it is not transparent to. What kind of material does light pass through?